Hello and welcome to another lesson on GCSE physics. Today's learning intention is to know how the current through a bulb affects the potential difference across the bulb, and that is one of the required practicals on GCSE physics and GCSE combined science. Today's success criteria is to identify the independent and dependent variables in an investigation, to draw a line graph to display the results of the investigation, and to explain the need for a safety resistor when using a diode as part of the investigation. Now, the first thing that I want you to do is think about what the independent and dependent variables will be for this investigation, bearing in mind, of course, that we are looking at how the current through a bulb will affect the potential difference across the bulb. So please pause the video and state what the independent variable and dependent variable will be. So the current through the bulb will be the independent variable because that is what we are changing, and the potential difference across the bulb is what the dependent variable is, which is what, of course, we are measuring. Now I would like to have a go, please, at listing all of the equipment that we need to carry out this investigation. They could in the exam ask you to write a full equipment list for this required practical, or they could ask you to complete a partially existing equipment list. Now, as part of the equipment list for this experiment, we are of course going to require a bulb because the whole point of this is to investigate how the current through the bulb affects the potential difference across it. But in addition to a bulb, we will also need connecting wires, which could also call connecting leads. We will need a voltmeter, of course, to measure the potential difference across the bulb, and we will need an ammeter to measure the current that is flowing through the bulb. In order to change the current that is flowing through the bulb, we'll make use of a variable resistor. You might see those called rheostats as well, but we'll just stick to calling it a variable resistor. And finally, we will need a power source, whether it be a power pack or a set of batteries. Now I want you to pause the video and draw a circuit diagram to show how you would set up that equipment. So when it comes to setting up this equipment, the first thing that I would be tempted to draw on my circuit diagram is of course the power pack or the batteries, which you can see I have drawn here. Now that is what is going to cause a current to flow, and to measure the current that is flowing through the circuit, we will use an ammeter, and ammeters need to be part of the main loop because ammeters are of course joined in series. We then connect that to the bulb that we're of course investigating, making sure to use the correct circuit symbol for a bulb, which is a circle with a cross going through it, and then we will want to be varying the size of the current through that bulb, so the final thing in the main loop is going to be a variable resistor. To draw that, we draw a regular resistor with an arrow going through it as shown there. Now, of course, we need to know how the potential difference is affected. Voltmeters, which is what we use to measure potential difference, have to be added in parallel with one connecting lead on either side of the bulb, and so the voltmeter is added as shown there. What I would like you to have a go at doing for me now, please folks, is pausing the video and drawing a results table that we will use to record our results. Please do remember that a good results table has got the units included in the headings. So for this results table, there are only two columns that we need. We need current and we need potential difference. Now current is of course measured in amps, so that should be labelled current / A, and then the potential difference needs to be labelled potential difference / volts. I've included as well some values in there so we know what range of current values to use, but you wouldn't be expected to do that until you've carried out a preliminary investigation. Now let's consider the method that we're going to use. The first part of the method that we would do is to simply set up the equipment as shown in that diagram. After we've done this, we would measure the current using the ammeter, and we would measure the potential difference using the voltmeter. Please remember that when you are writing a method, it is essential that you state what piece of equipment you use to make each measurement. So simply saying measure the current or measure the potential difference is not enough to get you the marks. You have to say using the ammeter and using the voltmeter. We would then adjust the current using the variable resistor. We would adjust it between 0 and 4 amps, and we would record pairs of values for current and potential difference. But obviously you've seen in the results table that I've drawn I want some negative values for current as well. To achieve a negative value of the current, we just simply reverse the connections on the power supply so that the current flows the other way around the circuit. We would then obtain a new set of data. Okay, so here is a set of example results because I assume that you're not watching this video in a laboratory, but this is a set of results that you would have obtained if you'd carried out the experiment yourself. Now, in terms of doing the analysis for this, there are 4 tasks that I would like you to do. The first thing is I would like you to draw these results on a line graph for me, please. Then I would like you to consider why a line graph is more suitable for displaying these results than drawing either a bar chart or a pie chart. Then I would like to consider how we can increase our confidence in the shape of the line of best fit of our graph. And then finally, consider how we will go about seeing if the results of this investigation are reproducible. So to draw a graph, all we would need to start off by doing is drawing a set of axes that has 4 quadrants on it like shown. We need it to be a 4-quadrant graph because the current is going to go positive and negative, and the potential difference is going to go positive and negative also. To get the first mark for drawing any graph, all you need to do is label the 2 axes, including a unit. So I've labelled the axes going up as being current / amps, and the current going across the bottom as potential difference / volts. If you haven't included units on those labels, you would be throwing away a mark at this stage. The second mark is for including a suitable scale. Now, neither the current nor the potential difference rise above 4, so because of the amount of graph paper I've got available, I can simply go up in 1s and fit all of the data points on there. The third mark comes for drawing the actual graph itself and plotting the points. When we plot points on a graph, it's essential that you do not do circles, dots or blodges because these aren't considered accurate enough. The most accurate way is to draw crosses, as you can see there on the board. Once we've got the points drawn, we then draw a line of best fit. When we draw a line of best fit, don't go dot to dot, which I know is very tempting. You have to look at the actual pattern. Starting by looking at the positive values, you can see that those crosses do form a sort of curved shape, and so we should be drawing a line of best fit freehand that is a curve that goes through as many of those points as possible, as you can see there. We would then do the same in the bottom left quadrant, and so therefore we can say that the IV characteristic for a bulb follows that shape. The second thing was, why have we drawn a line graph? Well, we've drawn a line graph because both variables are continuous. Current and potential difference can take any value, and so therefore we say that those variables are continuous. The third question that we're asked is how we can increase the confidence in the shape of that line of best fit, because obviously, as you can see, we've got parts of that graph where there's large spaces between crosses. How do we know that the shape is correct there? The way we can make sure that we're confident is by simply doing more readings but with smaller intervals. So instead of measuring every amp of current, we could have measured every 0.5 amps of current to see how the potential difference changed, and that would have given us more crosses, and so we could have been more confident about the shape of our graph. And then the final question that we were asked was, what can we do to make sure that our results are reproducible, or to see if they're reproducible? To do that, we will compare the results with other groups to see if they get the same pattern in their results. This required practical does require us to do this same experiment again, but with a fixed resistor. To do that, the method would be exactly the same and we will collect the data in the same way, the only difference being that the circuit would have a fixed resistor in it instead of a bulb. And then finally, we need to do this experiment once more, but instead of using a bulb, we would need to use a diode. Now, a diode is a much more sensitive piece of equipment than a bulb or a fixed resistor, and so it's essential that the current going through the diode doesn't get too large. To make sure the current doesn't get too large, we include an additional resistor in the circuit, which I've labelled there as P, and that resistor protects the diode by making sure that the current doesn't get too big. We're also using a milliammeter in this situation as well, because the current values we would expect to be much smaller than for the bulb and for the diode. Now, the results of those two investigations are shown on these graphs. As you can see for the fixed resistor, the current and the potential difference are directly proportional to each other. We can see that because the line of best fit is a straight line that goes through the origin. For the diode, we can make the conclusion that a diode will only allow current to flow through it in one direction, which is why it has that unique IV characteristic as shown on the board.